So the next talk is going to be about the following, and I'm quoting the title of it: "Talk to your camera to see better." So we would like to invite Professor Raja Giryes, School of Electrical Engineering from the Tel Aviv University.
Good morning, everyone. So my name is Raja Giryes. I'm a professor at Tel Aviv University, leading a group in deep learning. We're doing different stuff, ranging from images to vision language models. So all the talks before were on NLP, except for the first one by Yedid that talked on images. So I will return back to images, but we'll see how we can combine both, use both text and images. So this is two works by my PhD student, Giryes Yosef, and he also prepared the slides. So many of you saw things related to generative models that you give a text and then you generate an image. So for example, here you have an imagination of the AI week being held at the beautiful forest on the moon on the left, and you have an image of you sitting there. I don't know if you find yourself in the crowd. But, and then the question is whether we can use this to do better imaging. So all of you today use your phones. I see some in the crowd taking photos. And the question is whether we can use combined language in order to take better photos. So in order to understand how we can use all these generative models to take better photos, so let's understand a bit how all these diffusion models, these models that generate these beautiful images, how they work. So basically, they use a very simple concept. What they do, you start from a clean image, the face that you have here. You add to it a small amount of noise gradually till you get total white Gaussian noise. And then you train a neural network that is trained gradually to remove the noise bit by bit till you get to the clean image. Now, and then what happens in addition is that you use another model that is called CLIP, which align image and text, bring them to the same space. And the neural network that is removing the noise bit by bit is getting some textual information about the image that you want to reconstruct. And in this way, you are able to get such nice images just by giving a sentence. So basically, you start from total noise, you remove noise bit by bit by telling what type of image you want to get, and you get the image that you want to generate. So what we thought about is, okay, so maybe we can change the way we take images. Instead of just taking a click and then capturing an image, maybe tomorrow you can also tell your phone what you are taking a photo of, and then improve the way you do imaging. And I think it's very helpful, for example, if you have your kids and you took many photos of them, but now you want to take it at night in front of the Eiffel Tower, so it's very hard because they move a lot. But if you tell the phone that this is your kids, probably it will be able to reconstruct them better. So the way we go is that we use this diffusion model that I mentioned before. We have this clip embedding that I told you that basically take photos that embed images and text to the same space. And then what we can do, we can say, okay, so we can take a data set of images and captions. We can add noise as in the real world, train a diffusion model such that it will reconstruct things depending on the noise. But the problem is that if you try to work with such, to use it with real cameras, so we have something that is called domain gap. Domain gap means that many times when you use AI or neural networks to process real data, so the data that you use in your simulated data or in your theoretical data doesn't match the world. So the question is how I can train a diffusion model using simulated data and then use it with my phone to take real images that are guided by text. So the trick that we did is we took a phone, we took a computer screen, and then we projected on the screen many photos. We captured all of them with the phone. And then because we projected the photos, we know the ground truth. So we start with the simulated data, then we fine tune, we generate our data set by just projecting images on a computer screen. We capture everything, and then we fine tune the diffusion model with LoRa. LoRa is a simple technique that you have low rank matrix that you add to the weights of the network, and then you can fine tune things very efficiently. And then there are two important stages in the process. So the second one that I mentioned is closing the domain gap by generating real images. The first one is how we can make the simulation of the imaging very accurate such that the adaptation will be easy. So the way to go is to try to estimate how real noise behave. We take a standard way to model real noise is combination of Gaussian noise and shot noise. We modify the diffusion process to work instead of just Gaussian noise to work with the Gaussian noise and shot noise. We train it, and then we can work with, we can take noisy images and get great reconstruction results that when we give text, we get much better results. So here you can see an example of simulated data. Here there are two competing techniques that don't use diffusion. When you use diffusion, you get much better reconstruction. When you add text and tell the model what it sees, you get much better the details. Here you can see results from the screen. So basically, these are results of real images. Here you can see the sign. We reconstruct it much better. We reconstruct the bear here much better because we tell the model that it's a bear. And of course, we don't just work on the screen. We work with real data. And here, the student terrorist went to the street, captured different objects. And you can see that our model that was just fine-tuned with a computer screen can reconstruct an object much better with the diffusion model, both with text and without text, but with text we get much better results. So this is something that we did with regular camera. But one of the problems when for phone manufacturers, that if you look at your phones, you have these cameras that are going up. And the reason for that is that you have the form factor of your camera, and you have a distance between the lens and the sensor that force the camera to be very large. And then the question is whether we can do imaging without a lens. If we can remove the lens, we can make our cameras much smaller. And this concept is called flat cam. In flat cam, basically we replace the lens with a diffuser. It's a small random amplitude mask very close to the sensor. And in this way, we get measurement of the world, but it's very noisy. So flat camera is an approach to get very tiny imaging devices. We use a separable mask. It's a random mask that we put very close to the sensor. I will show an image of it in a bit. And the nice thing is that you can model it with a linear model. Basically, you can write also the theoretical, the PSF of the imaging system, and you get an image that is the result of the original signal convoluted with some PSF. Now, some of you will say, okay, so it's a very simple deblurring problem because it's convolution, but in reality, this is how things look like. So here you have the sensor, here you have the mask that you can see that it's a random amplitude mask, a separable random amplitude mask. And then here we have the scene. We capture the scene, and this is the sensor measurements. In regular imaging, the sensor measurements is visually related to the scene. Here, you can see it's more related to the pattern that we put. And if we just do the convolution, then this is the reconstructed image that we get. And clearly, this is not what we want to get. And if you use some tricks, it improves. But then the question is whether we can use the same thing. So we have diffusion models that model all the world. They saw every possible image that we can think about. Why not tell the camera what it sees and then help it to get much better reconstruction? And we use the same thing. So in the previous work I showed you, we just trained the diffusion model from scratch. In this model, we use a pre-trained latent diffusion model, stable diffusion, the one that it's the strongest open model for image generation. And we use control net to fine-tune it for our type of measurements. So we take our measurement, we apply the separable transform that give us the horrible reconstruction. We put the horrible reconstruction in the control net. We fine-tune it such that, given the text and the measurement, we get the target image. And we train that. Here you can see the result. Here you can see our prototype flat camera. You can see that we are very professional in tighting things. Here you can see the captured image, the mask pattern, and the measure PSF. And here you can see also the gap between theory and practice. So in theory, we have the mask pattern that is perfect, etc. But if you just try to use that, things will work horrible. What you need to do is you need to measure the real PSF, take this real PSF, return it into your model, fine-tune your model. And here again, we see the importance of when you want to design something for the real world, you need to measure things for the real world, bring them back to your model in order to improve your results. And here you can see some of the results that we get. So here, this is the prototype measurements. These are the reconstructions that we get. And below, you can see the ground truth images. And here, these are the results with text, the results without text. And the text adds some details that are important. If we compare to prior work like FlatNet, we get much better results in all in all the measures. And here you can see some comparison on simulated data, which is not really interesting because it's simulated data. But the interesting thing is that we can take our model and apply it on real-world results. We took this prototype camera that we built. We captured different things in the lab and outside. We captured this image, this T-shirt. We captured this plant, and you can see that when we say that it's a plant with green and yellow leaves, we get, or that we have here black palm tree and the red, orange, and yellow background, we get this reconstruction. Now, if you will notice here, so we get, I think, nice results, but we have the same problems that was mentioned in the previous talks that we need to deal with, and it's like one of the limitations and one of the future work. As you have hallucinations in LLMs, you have also hallucinations in diffusion models, so you have hallucinations all around. This is one of the challenges that we suffer from both in text and images. Here you can see another example. And this is like one failure case. We have a red shirt Football Club Barcelona, yellow banana, red, green, and blue colors cup. And this is the reconstruction that we get. So, but you can see here that basically by adding text and using diffusion models that solve the whole world, you can get quite good results from measurements that look like that. So even if you have the worst camera in the world, if you can tell it what you see, basically it will show it to you. So thank you very much, and I will be happy to answer any questions.
Questions? Yes, we have here a question.
For example, your kid in with the Eiffel Tower, what is the difference between optimizing the picture of your horrible camera and generating a beautiful picture of your kid in the night with Eiffel Tower?
Yeah, so I think that this is, maybe I should have added this slide. So while we were working on this work, there was a meme of a totally lensless phone. So someone took a phone with the GPS and then captured the image, and then the phone, according to the GPS, reconstructed what is around according to Google Maps. So, so of course, you have this trade-off between just generating things that you tell the phone and like combine knowledge and capturing the exact moment. And in some sense, we want to know how to balance that. So you want to capture the exact moment. And when you measure things from the world, you have something related to the exact moment. But something is lost because of the light, because of the movement. And the phone and the world knowledge that you have about your child, about the scene, about the place, can help recover all these details. So we don't want to fake that. So you know that some people go and fake images to show everyone on Instagram that they are so great, but they have miserable life. Or we know that they create some problems that what we see is not what we perceive is not the real world. But so we want basically to try like to give you the real information, but to use prior information to reconstruct it better.
Okay, more questions?
Yes, I have a question. I saw that you presented a stop sign. Is it like a solution to solve the text. We know when we're asking to generate a text for those model image generation, the text is not like a triangle. It's not like the original text we asked. Is it going to solve this problem?
So generating text with a diffusion model in an image is something that is still challenging. So here, this is generated by DALE 3. You can see here that it generates really bad text. But the neat thing in our work is that we propose a general framework. And then so also in our reconstruction, the stop sign text is not reconstructed very accurately. But once the diffusion models will advance and reconstruct better the text, also our reconstruction will improve further. So basically we propose a general framework that when diffusion improves, our framework will also improve.
Okay, next question. We have another one on the other side, so you will need to pass it really on the other side.
Hi, this is kind of on the same topic of text, but less in generation and more in denoising. Do you think you could use the model, or have you tried to use the model to denoise images of text in a way that keeps the text actually real and readable, and maybe even the same for other context-specific objects like faces or even buildings or cars?
So this is something that you can do with ControlNet. So it's not something that we exactly did, but if you use ControlNet and you can fine-tune ControlNet such that you give it the text and then you teach it to keep the text in the exact places. So you can integrate it in our framework, but we didn't do that.
And we have last question.
Hi. Yesterday we discussed a lot the legal status of AI-generated images, and that was an idea that the image should be certified in real time when it is made by camera phone. So what is the legal status of such an image?
So in this case, we try to capture reality. So to my understanding, this should be regarded as real image. This is not generated. This should capture the real world. And then maybe if you want to have the legal status, so in legal perspective, if you want to keep authenticity, you need in this case to keep both the raw and the reconstructed image, such that if you spread it, people can compare the raw and see what was the raw information.
Thank you very much, Professor Raja. Amazing talk.